So this video is a collection of comments made in the online class question and answer session that was held just a little while ago. And the first question I was asked was to go over moments and moment generating functions. So of course we know that e of x is the first moment. We know that e of xn is the nth moment. Right, and then here in chapter 9, we invented the MGF, the moment generating function. So you have a random variable x, and maybe it has a PDF, or actually it could also have a PMF, right? And the moment generating function of this random variable is phi, subscript the name of the random variable of a variable called s, right? And it was equal to the integral minus infinity to infinity. And we'll work with densities, but you could do everything with sums. E to the sx dx. So so in one way, right, you could think of this as, oh, we had a general expression for, oh, the moment, the expected value of any function is this. So this moment generating function, this g, is exactly this e to the sx. And so another expression for the moment generating function is expected value of e to the sx, right? So this thing is when this was a course for juniors and seniors, I could just simply point and say, this thing is the Laplace transform of the PDF. And you'd be like, oh, yes, it is. Why, of course, right? And nowadays, it's like here with sophomores, it's not so clear. Like maybe you've seen Laplace transforms. If we do this at the end of the semester, like you've all to be finishing Principles of EE2, and I think you've all seen a Laplace transform. So how about this? Like, reply in chat, yes or no to if I've seen a Laplace transform. We got a yes from Mohammed. Yes, yes, yes. See that? Sometimes though, other years. No, Laplace transform's good, Adrian. Like, um, um, Laplace transform gives you this frequency domain representation of signals, and uh, it is precisely this representation that lets us feel morally superior to computer scientists. Computer science people don't care at all about Laplace transforms, about frequency domain, and electrical engineers kind of adopt that as kind of their core thing. Uh, so uh, uh, so in fact, you should embrace that we're seeing a Laplace transform yet again. I'm wait a minute. Watch this. I'll turn on my other camera. Maybe this is better. So you can see I'm smiling, huh? I don't know if you can see my other face. Okay, so I'm sleeping. The face that's doing the writing is the sleeping Roy, and this Roy here is smiling about talking about how great it is that we're all Laplace transform people. See? Yeah. Okay. what we have here, right, is this Laplace transform, and when this moment generating function has these magical properties. So for instance, um, like if we take a derivative of the moment generating function with respect to s, we have d ds of this integral. But the integral is with respect to the variable x, right? And this derivative is with respect to the parameter that's inside. And because a PDF is kind of a well-behaved function which has area underneath of it, one, it's absolutely integrable. You can exchange the differentiation and the integration, and you get this. Right? And now when you do that, so you get, uh, and so this derivative inside here is derivative with respect to s. And so we do this for every value of x. And so inside this derivative, the x acts like a constant. And uh, I'm about to sneeze. Wait a minute. Okay. So so in fact, the thing inside the box is x e to the sx dx. And now if we look at this expression, we can look what at this integral and say, oh wait, I can now set s equal to 0, and this e to the sx term will be uh, equal to 1. And the result that I get is at s equals 0, the quantity in the box is just x dx. So I have uh, PDF times x dx integrated over all x, and that's just equal to the expected value of x. And you can keep repeating this step so that, so for instance, the nth derivative, uh, no wait, the n goes here. I hate the thing is this has two erasers, and I can never understand what the other eraser does. Uh, if you do that, you take this derivative n times, and you get and set it equal to 0, you get e of x to the n. So I think we can do some examples of this. So okay, so we'll do an example where x is, this is an example where it's easier to do it the regular way. How about uniform from 0 to 10, right? And so the PDF of x is equal to 1/10, 0 less than or equal to x less than or equal to 10, 0 otherwise. And now the moment generating function, I have the wrong thing. So the moment generating function is equal to the integral e to the sx times the PDF dx, which becomes the integral 0 to 10 e to the sx times 1/10 dx, right? So now this is an integral over the variable x, and now here we think of s as just a fixed parameter, right? So this is equal to 1/10 1 over s e to the sx, right? We take a derivative of this with respect to x, and it cancels out the s comes down and it cancels out the 1 over s, right? And so this is evaluated at 0 and 10. So we get 1/10, 1 over s e to the 10s minus 1 over s. So I guess I'll write this one more way. It's e to the 10s minus 1 over 10s. I think that's right. Okay, so we could now use this to calculate some moments. It's a terrible way to do this problem, but we can indeed do it. So I'll change my pen and use some more. So if I take a first derivative of this, well, I guess I have to do derivatives in front of you. So it's the bottom times the derivative of the top minus the top times the derivative of, I guess I should have left the 1/10 out. So maybe I'll erase that. See, are more people showing up, or are you guys giving up on me? I can't really tell, actually. Oh, there's 9 people here. All right, that's good. Okay, so there's a 1/10 out in front, and it's the bottom times the derivative of the top, which is e to the 10s times 10, minus the top times the derivative of the bottom, which is just s, which is 1, all over s squared. And so this equals 1/10 of, okay, so I think I have 10 e to the 10s over s minus e to the 10s minus 1 over s squared. uh, Okay, so this shows why this is a terrible example, and you'll see this example is not in the book, and it's not in the book because something dreadful, I think, is going to happen here. I wonder if I made a mistake somewhere. Da, 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 da. So the thing is, we're going to evaluate this at s equals 0, right? And I see like I was expecting to see a 0 over 0 and have to do some L'Hopital's rule nonsense. But I don't see. I feel like that's the way it usually works, but I feel like I've made a mistake here. Okay, so since I maybe have made a mistake, let's go back and check everything since you guys are in for this. My definition is correct. My integral is correct. This is 1/10 1 over s e to the sx, yeah, from 0 to 10. This is, there's a 1/10, there's a 1 over s, that's fine. I should have e to the 10s minus 1. This expression at s equals 0 evaluates to 0 over 0. But if, for instance, we took L'Hopital's rule and took a derivative of the numerator, we get 10 e to the, okay, I think everything is still recording. So if you take a derivative, you get 10 e to the 10s over 10. And this equals 1 at s equals 0, so that's okay. And so now we take a derivative of, Mohammed says, oh, I do get 0 over 0 in the last thing I wrote. I have to admit, I don't see that. Like I see 10e to the 10s, right? And then I see, oh, I see this goes, okay, so, okay, Mohammed's right. This shows you why office hours are terrible and why professors prepare. Okay, so Mohammed's point is that I should write it this way. It's 10s e to the 10s minus e to the 10s minus 1 all over s squared. And so, yes, he's completely correct. I just should have remembered to be like a third grader and use a common denominator, right? So the s makes this term go to 0, and this is 1 minus 1, which is 0. And so now we're ready to we want to evaluate this 0 over 0 by taking L'Hopital's rule, right? And uh, and so in that sense, we now take it's 1/10, and now we'll take a derivative of the numerator. So derivative of the numerator is 10 e to the 10s by taking a derivative of this s plus 10s times 10 e to the 10s minus 10 e to the 10s, right? Over 2s. So this 2 is where we're going to get our answer from, right? And now if you evaluate this at s equals 0, I think you will get 10 plus 0 minus 10. It still evaluates to 0 over 0. So we have to do L'Hopital one more time. uh, so this is kind of evil. So we'll do it again. And so this is equal to 100 e to the 10s, right? Plus 100. And we have to take a derivative of s times e to the 10s. Okay, so it's 100, and it'll be e to the 10s plus 10s e to the 10s, right? And then we'll subtract minus 100 e to the 10s. And here, the s in the denominator, the 2s will have derivative equal to 2. And if we evaluate this expression at s equals 0, so let's take a break here. So how many people think I'm going to get the right answer? We all know what the answer is. The answer is 5. All right. Well, no confidence here. Come on, guys. All right, so I have 1/10. I get 100 plus 100 times 1 plus 0 minus 100 all over 2. So I think I'm kind of golden here. This 100 cancels that 100. And this is 100, but divided by 10. And this is divided by 2. So the answer is 10 divided by 2. It equals 10 over 2, which is 5. And of course, 10 over 2 is exactly the old a plus b over 2 formula with a equals 0 and b equals 10. And we get exactly the correct answer. So there's a little bit of a lesson here, and the lesson is that um, the examples in the book where we use the moment generating function and take some derivatives and everything is peachy, um, they're kind of like fraudulent examples in the sense that they're carefully chosen to show how nicely it can work in some cases, this moment generating function. This way where, oh, you take some other thing and you you get a moment generating function. When you take a derivative and go to set it equal to zero, you get a 0/0, and then you do L'Hopital some number of times. Like this is not an exception. This happens a lot, right? But in fact, if you go through all of the machinery, you get the right answer, um, and that's not so bad. Okay, so I'm going to pause this video and go to a new page. The kind of example that appears on some old exams was something like this. It was like random variable k has MGF, and I might say something like phi k of s is equal to 0.1 plus 0.2 s plus 0.3 s squared plus 0.4 s cubed, right? And then I might ask you some questions about that, right? And the first thing you should do is like be like, okay, is this really a moment generating function? So if you check phi k of 1, right, you'll see that it's 0.1 plus 0.2 plus 0.3 plus 0.4 adds up to 1, you're good, right? The next thing you want to realize about this moment generating function is that, of course, it's also, you know, because we have a discrete random variable here, it's equal to a PMF. Oh, wait, I made a mistake. I'm really sorry. I'm gonna erase some stuff. This is not, there's a different formulation. This is supposed to be an e to the s, an e to the 2s, e to the 3s. If you were sitting at home being confused, um, apologies. The reason it's easy for me to make this bit of confusion is that uh, there's another kind of way people sometimes write MGFs for discrete random variables, where they do something that's equivalent to a Z transform. So if you've taken a discrete like signal processing course or a DSP, you'll have seen a Z transform, and you'll sort of realize maybe what stupid thing I was doing wrong. Okay, so uh, so now we fixed the last example, and this moment generating function you can also think of as e to the sk, right? Because in fact this is the expression for the expected value of e to the sk. And so the thing is, if you look at the terms of this summation, right, and you look at this expression, you realize you can match things up one by one. And what I mean here is that, for instance, if this starts, say, at k equals 0 to infinity, like I have pk of 0 e to the s0 plus pk of 1 e to the s plus pk of 2 e to the 2s plus pk of 3 e to the 3s, and plus there's more terms, but in fact all those pk's are going to be 0. And so you can just read off the correspondence, because this e to the s0 is equal to 1, and so this pk of 0 is this 0.1, and this pk of 1, oh, is this, sorry, it wasn't that 0.1, is this 0.2. Let me correct this. This pk of, oh, wrong color. See, I gotta get so fancy. Okay, I'll go back to the right color. So this pk of 0 is this 0.1, right? Because e to the s0 is equal to 1. And pk of 2 is equal to 0.3. And pk of 3 is equal to 0.4. So for instance, I could ask you, given this moment, I pointed my other screen, given this moment generating function, I could ask you what's the PMF of k, right? And you would be able to simply write down pk of k is equal to 0.1 at k equals 0, 0.2 at k equals 1, 0.3 at k equals 2, 0.4 at k equals 3, and 0 otherwise. So, and now if I take a derivative of this, right? The When you work in discrete PMFs, like these derivatives are really simple, right? So the derivative of 0.1 of this term is, of course, 0. So it's equal to 0 plus 0.2 e to the s, because the derivative of e to the s is e to the s, plus 0.3 times 2e to the 2s, plus 0.43 e to the 3s. And now when I evaluate at s equals 0, I get 0 plus 0.2 plus 0.3 times 2 plus 0.4 times 3, right? And this, you can just see this is exactly the same thing as k, pk to the k, for k equals 0 to 3. So that's the expected value. So, uh, it seems as though in recent exams, knowing how to translate this kind of an MGF for a discrete random variable and either find a PMF or find an expected value, it's something. I'm going to see if I have more. I realize I didn't have any more questions. That's something I've sort of asked just to make sure that you've read chapter 9. Okay, so we had a request to look at example 6.4. This is one of the historically tricky examples in the book that generates a lot of questions. And in some way, the setting is simple, right? We have there's something actually very confusing. So I think, okay, so there's something wrong with the example. I have to show you this first. This reminds, start my recording again. So we had a request to look at this problem here online, and I was just went kind of out of the recording to point out that the problem statement says -1 to 1, but in fact the solution works this out for x continuous from -1 to 3, and this 3 makes things a lot more complicated. And to prove that, I'm going to work it out for the -1 to 1 interval, and you'll see there actually things are kind of simple. So we know the PDF of x, it's equal to 1/2 for x between -1 and 1 and 0 otherwise. And so I have a picture of that PDF. Looks like this: -1, 1/2 fx of x is x. Looks pretty good.
Hello.
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 So Princess Poppy just came in. All right. So okay. So now we have w. and W is equal to X squared. And we ask you to find the CDF, FW of W, which is the probability W is less than or equal to W. And and now let's pause for a second and ask what values of this is this easy? So, okay, hold on a second. Hey, hey, Dada, could you kind of go somewhere else with her? Because I'm actually trying to do a lecture here.
But
Yeah.
I have to come back.
Yeah, yeah.
Hi, what you doing?
I don't know.
I didn't either. Let's go downstairs.
Princess Poppy is now going out.
Princess Poppy.
All right. So, okay. I think that Trolls movie was terrible, but she really liked it. So, I don't know. I guess I'm just old. Okay, so let's get back to work here. So W we know is going to be greater than or equal to 0 because it's equal to x squared. So the CDF of W is equal to 0 for W less than 0. So the interesting region here is W greater than or equal to 0. And so now we say, oh, this is the probability x squared is less than or equal to W, right? And if you just work algebraically, uh, um, this you can say, oh, is the probability that x is between minus W and W. I'm sorry, minus the square root of W and the square root of W. So this is the first critical step, and I guess I'll ask John, like, okay, are you okay with this step? Okay, that's good. Okay, so this step is true kind of no matter what the PDF of X is, right? Like so far we haven't used any information. It just has to do with the function x squared and the way it's a kind of a nice bowl that's symmetric around the origin, right? And we can go do another step. We can say, well, this is the integral minus the square root of W to the square root of W of the PDF of X dx. And that step is also true for every random variable X, right? Everything that's tricky, it only becomes tricky when you actually plug in some kind of a PDF in there. Okay, so now we have a PDF, right? We have this PDF, right? And the question is, how do we evaluate this integral for this PDF? And uh, we can kind of work two ways here. Like there's one case that's kind of obvious, right? And that's if W is greater than one, right? If W is greater than one, then if you know that X is uniform from minus one to one, then you know that X squared is always less than or equal to one. So So this is kind of like the other half of the easy cases. So I'll just write some words. Because x is between minus 1 and 1, w equal to x squared is less than or equal to 1. And because of that, then the CDF of w is equal to 1 for w greater than 1. Like the probability w is less than or equal to 2 is 1. Right? The probably w is less than or equal to 3 is 1 because x squared is never bigger than 1. Okay, so and that's kind of the other easy case that you can argue. But now you're left with the case, and I'll switch ink just for fun, where W is now like between 0 and 1, right? And in that case, this integral, you know the square root is between 0 and 1, and you have like a case like this, like here is square root of W, here is minus the square root of W, and this square root of W is between 0 and 1, minus the square root of W is between -1 and 0. And now we're doing this integral with these limits, and in fact, the integral is equal to this area under the curve that I'm highlighting in this blue, right? And times the density, actually it is the area under the curve. So I guess I'll choose. So this is minus root W to root W 1/2 dx. And this is equal to square root of W. It's really 1/2 x, root W minus root W. Okay, so uh, so we kind of have, for this case, the full answer here, right? So we have a PDF of x, and it looks like of W, and it's equal to 0. Then it's equal to the square root of W, which I think here is 1. Here is 1. Looks something like this. This thing just touches at root, and now it's a straight line. Okay, so this was pretty simple, right? But it was simple because um, these limits here for the PDF of x, like x can be negative, but it was over a symmetric range from -1 to 1. So as long as the range is symmetric, like minus something to plus something, like this whole calculation is pretty straightforward. So John, you agree? Like, okay, yeah, that seemed pretty okay. It was not as confusing as the incredibly complicated thing I did. I think I did this in one of the lectures. Uh, like where I actually did a much better job in the video than I ever do in class because I spent an hour making corrections to myself. Yeah, yeah. Okay, so let's go do the real example. All right, so the real example, which doesn't have the simplifying typo, I'll try to find another page. Okay, so the real example was uh, x is uniform from -1 to 3, right? So this PDF looks like. Can you guys hear Princess Poppy crying in the background? Cry, cry, cry. She's actually a very happy girl. She's like the happiest person in our family. Okay, so now the value of the PDF is 1/4. It goes from -1 to 3, right? And the first set of steps are all the same. Like W is x squared. The CDF of W um, is equal to the probability W is less than or equal to W. And this ends up being the probability X is between minus root W and root W. Okay, so the first set of cases, I'll use red ink here. Like if I have root w between -1, actually, okay, wait a minute. I want to erase this. So of course, like we're only thinking about this. When we write this expression here, the square root of w is always a positive square root. Okay, so so now, like we'll do the case where w is first between 0 and 1, right? And in that case, the limits of like we have this, it's kind of just like we had before. Like the lower limit minus root w is bigger than this -1. And so now in the red ink, we do this integral. This probability is the integral from minus root w to, so okay, so this is, I'm going to switch black ink. This probability is always this, right? So what I wrote here in black, this is always true. But now we're translating this for different values of root w. And we're doing first in the red, this case, root w is between 0 and 1. And we write this integral and we realize, oh, it's the integral from here to here. And this minus root w is bigger than -1. And so this is minus root w to root w 1/4 dx, because the value of the PDF is 1/4. And this will be 1/4 x root w minus root w. So it'll be root w over 2. Okay. Then the next case is w is bigger than, root w is bigger than 1, but less than or equal to 3. So I'm using blue ink here. And then this is like a case where the minus root w is over here, and the positive root w is here. Like root w is less than 3, and the probability that we're trying to integrate, right? We're still doing this integral over here. I have to learn to not wave my cursor so fast, my little star. But this lower limit is in the range where this PDF is 0, right? So if I'm being super explicit, like there's a part of the integral here from minus root w to -1 where this PDF is 0, and so the actual integral where things are non-zero starts at -1, and then it goes all the way up from -1 to root w, and then you integrate 1/4 dx because that's the value of the PDF over that region. So you have 1/4 x, evaluate -1 and root w, and you get 1/4 root w -1. And it's kind of good to check, like this formula at root w equals 1, which is w equals 1, should give you, I'm pointing with my this this formula at root w equals 1 should give you the same answer as the red formula at root w equals 1. So the red formula is a half, and this formula is, did I make, so I made a mistake. Okay, I'm gonna see if I have some scroll down here to see if anybody noticed it. So I did this, it's 1/4 x, it should be root w minus -1. So indeed I did have a mistake. It should be +1 here. right? So now when I evaluate this formula at root w equals 1, I get, which is w equals 1, I get a quarter of 1 plus 1, which is a half, which then matches this at w equals 1, and I think I'm pretty good. So now I can write, uh, so there's just one more case to do, which I'll do very quickly. It's the case that root w is greater than 3, right? So now you have something like this. Root w is bigger than 3. Here's minus root w. And the probability w is less than or equal to w is, we're integrating, it's still this integral, right? But we're integrating from back here all the way up to here, right? And we have all of this 0, and then we have a region we get 1/4 from -1 to 3, and then 0. So this is equal to -1 to 3, 1/4 dx, and of course that equals 1. And you should have actually known that because root w, right, is bigger than 3 if and only if w is bigger than 9. And since x can't be bigger than 3, x squared can't be bigger than 9. And so the CDF should be 1 in that region. So you put all these pieces together and you get um, excuse me. This is 0, w less than 0. It's square root w over 2 for w between 0 and 1. It's equal to 1/4 square root of w plus 1 for w greater than 1 less than or equal to 3. No, that's a mistake. So uh, that's a mistake. This is actually 9. I'm using the wrong coloring, but I guess I don't care. Look, this was the limit, root w less than or equal to 3, but you translate that into w less than or equal to 9, and then 1 for w greater than 9. Okay, so that's the complete answer, and I think like doing it once with limits -1 and 1, and doing it the second time with limits -1 and 3 is a good demonstration of how like this step can be this step here, CDF of W, probability W less than W, probability X squared less than equal to W, translating X squared into the probability X is in this interval. That's all pretty simple. This is pretty simple, right? It's true. But now this gets complicated depending on what kind of PDF you write here, right? It's a different answer for every PDF. And so for some PDFs, this is quite complicated. So let's do one more example of this. Let's suppose that x is exponential, right? I guess we could carry around a lambda, right? Exponential lambda. So here's a PDF, right? And we know that it's lambda e to the minus lambda x, x greater than or equal to 0, 0 otherwise. Here's x, here's the PDF, right? And now I say find the CDF w equal to x squared. So actually, this is the problem. It's actually a wireless communication power problem. There's kind of models for wireless communication, wireless fading channels, where you have an exponential channel gain parameter, and then you have that thing squared to give you a received power. So if you eventually take some wireless communication course, you'll have to do some kind of problem like this. All right, so we're interested in this CDF of W equal to x squared, and we just start with the usual steps. This is probably W is less than or equal to W. That's the probability x squared is less than or equal to W. That's the probability that x is between minus root W and W. All of that is still perfectly fine, right? But now, um, when you go to do this integral, and then, okay, so here is the integral. This is still correct because we haven't specified what this PDF is yet, right? So now this is only an interesting problem when, so root W is positive. So here is root W, here is minus root W, and we're integrating the PDF from here to there. But this first section from minus root W to 0, the PDF is 0. So in fact, we're doing, it's really just this integral we're doing. Right? So this ends up being the integral from 0 to root W, and then it's lambda e to the minus lambda x dx. And of course, this is minus e to the minus lambda x from 0 to root W. And this is equal to 1 minus e to the minus lambda root W. Okay, so if we took tried to find a density of this, right? Like density would be PDF of W. Let's actually, no, we shouldn't find a density yet. We should first finish what this problem is. So this is the right solution for all W greater than or equal to 0, right? And a moment's thought says, oh, if W is less than 0, then the CDF should be 0, right? So we get a complete expression for the CDF. It's 1 minus e to the minus lambda square root of W, W greater than or equal to 0, 0 otherwise. And then if I wanted to find a density function, I just take a derivative and I get dw of the CDF, and try not to embarrass myself. So this is equal to minus e to the minus lambda root W, then times the derivative of the exponent, which will be minus lambda times 1/2 W to the minus 1/2. Right, so I get lambda e to the minus lambda square root of W over 2 square root of W. And this is for W greater than or equal to 0. And this is actually not the thing I thought we were going to get, but it is the correct answer. So I guess the reason I just did this example, John, is to say that like this example is pretty simple, like, but still, once you go from this step, which is always true, you have to look at this PDF, and so in this exponential case, it's only non-negative, And so this half of the integral disappears and you're just integrating here, right? And now you get some answer that reflects that. All right, so stop